Good afternoon, everyone. I'm Nguyen. I'm here to present our work called Chopper. Chopper is a diagnostic tool that explores file system design problems. Currently, it focuses on the problems that lead to low latencies. Latency is important for interactive services running in the data center, such as instant search results and Google Glass. But it's very hard to maintain low latency because as the TLS paper pointed out, temporary high latency episodes that are not important in small scale may come to dominate overall service performance at large scale. And this animation illustrates the idea. A user's request can only finish when all the sub-requests are finished. If one request takes a long time, then the user has to wait. So it is more important to avoid low latency at every node in the data center. Local file system is a critical contributor to the tail latency. Local file systems such as Linux exe4, XFS, and ButterFS, they're the foundations of many distributed file systems. If the local file system has low latency, then the distributed file system built on top of it will suffer. So it's important to avoid low latency in local file systems. To address the latency problem, we have built Chopper to discover the high latency operations in local file systems. Currently, it focuses on block allocator, which determines the data layout on disk. Bad data layout can lead to very long data access latencies. For spinning disk, it leads to more disk 6. For SSD, it leads to more time-consuming garbage collections. So the goal of Chopper is to find the problematic corner cases in the file system block allocator. The challenge is the file system has a very large input space. For example, there are so many ways of writing a file. Which one should you pick to trigger the corner cases? To address the challenge and accomplish the goal, we use statistical techniques to explore the file system and find the corner cases. We believe there are three major contributions. The first, we provide an overall analysis of file system block allocations. Second, we have analyzed the unexpected behaviors in detail. Third, we have found and fixed for allocation issues in exe4 and significantly improved the allocation. There will be three parts of this talk. In the first part, I'll talk about how we exercise the file system in order to collect some data. In part 2, we analyze the data collected from part 1 and find out the problem of the file system. In part 3, I go one step further to find the root causes of the problems and fix them. Now I talk about how we exercise the file system and collect some data. First, we describe the workload and the file system by over 10 factors. These factors are going to be introduced right after this slide. After running the workload on the file system, we use a metric to measure the layout quality of these files. The metric we use is called data span, or dspan. It is simply the distance between the first physical block and the last physical block of that file. Smaller dspan is better. This slide shows all the factors that we use to describe the file system and the workload. They form a very large input space, which make it very hard to find and understand the corner cases. With such a large space, exhaustive search is impossible. For example, there are just too many disk sizes and file sizes you can try. To adjust this problem, our first step is to refine the space of each factor to a realistic subset. For example, we refine disk size to 264 gigabytes. We refine disk size to 816 to 256 kilobytes. If it takes 1 second to finish one combination of all these factors, after refining, it still takes 250 years to explore the combinations. To explore the space efficiently, we use a sampling method called Latin Hypercube Sampling. But before I introduce Latin Hypercube Sampling, let's look at random sampling first. In this example, there are two factors, disk size and the file size. For each factor, there are 4 values that you can choose. The big X characters in the figure are the samples chosen by the random sampling. A problem of random sampling is that it may leave some space unexplored, such as disk size of 2 GB in this case. Also, having 2 samples for disk size of 8 GB may confuse people when you visualize data because it may appear to have more problems than other cases. Now let's look at Latin Hypercube sampling. Latin Hypercube sampling guarantees there is only one sample in each row and each column. If you follow the highlighted rows and the columns, you'll find that each time there is only one sample in the rectangle. So in general, Latin Hypercube sampling explores the space evenly, and it helps visualization. Also, it explores the interaction between factors well. For example, maybe certain disk size do not work well with certain file size, and we would like to find out those cases. With Latin Hypercube sampling, we ran 16,000 tests, which took about 30 minutes with 32 machines running in parallel. Now let's talk more about the data layout quality metric. We don't need this band to be a metric that highly correlated with the end-to-end data access performance. This band is simply a signal that helps us find out the allocation problems. Since this band only considers the first and the last physical block of the file, it cannot distinguish layout A and B on the side. An alternative is average block distance, which can distinguish this A and B layout, but it's just too complex. Another alternative is end-to-end performance, such as bandwidth, but such a metric has too many noise, and they are confounded. I find this band has the best trade-off between simplicity and the information gain. Now I describe how Chopper works. First, Chopper will create an experimental plan, and then it will do everything in memory in order to do all the experiments fast. It is okay to not use a real disk because we only care about the data layout, not the time. So to do so, Chopper will create a temporary file on the RAM file system, then a looping device backed by the temporary file. After that, Chopper will create the file system according to the experimental plan. And then Chopper can change the size of the file system or the use ratio of the file system. When the file system is ready, Chopper will run the workload on top of the file system and then use some existing file system utilities to find out the disband of the files just created. After that, Chopper will produce a data table with all the factors tested and the corresponding disbands. With such a data table, we can do statistical analysis to find out the problems of the file system. No kernel modification needed, and all the operations are in user space. Now let's talk about how we analyze the data to find out problems. First, we would like to see if there is a performance tail. So we use Chopper to test 2 file systems, XFS and exe4. We find that, and this figure shows the results. X is the disband, Y is the cumulative density function. We find that XFS does relatively well within the space we export, but exe4 has a very large tail. In our workload, the largest file is 256 kilobytes, but we find that 10% of the tasks on exe4 have disband larger than 10 gigabytes. So exe4 has some problem, and we'll study it in detail. Now we would like to see which factor influence the data layout the most. To do so, we can use a technique called factor prioritization. To understand it, let's look at the example on the slide. There are 2 factors, A and B. If you change factor A from one value to another, it doesn't change the disband. But if you change factor B from one value to another, the disband changes a lot. So in this case, we can say that factor B is more important than factor A. So by factor prioritization, we can get a ranking of all the factors that tells you which factor influence the data layout the most. Now I show you the ranking. People may expect the fragmentation and the user ratio of the disk to be the most important factors, but it turns out they are not. Instead, we find file size is the most important factor. This is surprising because in our workload, we only have relatively small files, and we expect the data of each file to be placed together compactly, but no matter how large the disk is. But here we find out that if you have a larger disk, the file will be spread wider. The second most important factor is file size. This is intuitive because the way we define disk-span. But we find that it influences disk-span much more than we expected. We also find sync, the different style of sync, write order of the file, and fsync are very important factors. This tells us different write pattern can lead to very different data layout. This is a whole list. And analysis such like this tells us many factors influence data layout unexpectedly. We have found many interesting behaviors of ext4. Here's another one. X is a different order of writing the file. Y is different way of doing fsync. And the red dots means a combination of those two factors sometimes produce bad layout. The green ones means that a combination always produce good layout. By visualizing like this, we find that there's a region that almost always produce good layout. Such analysis tells us factors may interact unexpectedly in ext4. And you'll see this figure later with more details. So we have found many behaviors that are surprising, and here is a summary. We find that ext4 may spread files wider on larger disks. We find file size are very important in determining the data layout. We find sequential writes can be harmful. We find sync and fsync pattern change layout a lot. And the fragmentation and the user ratio of this do not matter too much, and the factor may interact with each other. And you'll find more surprises in the paper. Now I explain the observations by going into file system details. All the unexpected behaviors in ext4 can be explained by 4 design issues listed here. And the paper covers them all, and this talk will cover the first 2 in detail. Now let's talk about the special end policy. Actually, the figure, the colorful figure you saw minutes ago can be explained by this policy. So this figure tells you if you write the end of the file first and call fsync immediately, you almost always get good layout. To find out the file system policies behind this observation, we studied several representative cases, and we find out the following. In ext4, there's a policy, what we call special end policy. The motivation is that if you are allocating the end of the file and the file is closed, the file system knows this file will not need any new space. So it allocates this extent with a special policy. The motivation is valid, but the implementation was problematic. So the non-ending content of the file and the ending extent are allocated with very different policies. These different policies jack the file apart to different locations on the disk, and so you see the large disk-span. Now let's see why a specific combination always have good layout. So in our workload, we divide the file into 4 chunks, and chunk order describe the order we write these chunks, and the fsync is a bitmap that tells you whether or not we do fsync for each chunk. In this case, we write chunk 3 first, and then call fsync immediately. For this chunk, condition 1 is true because this is the end of the file. Condition 2 is false because when you call fsync, the file has to be open. So special end policy is not true for chunk 3. And for the rest of chunks, condition 1 is always is false. That's because they are not the end of the file. So no matter whether condition 2 is true or false, special end policy is never triggered for these chunks. So this policy is never triggered for this file, and we can get good layout by avoiding this policy in this case. So to fix it, we simply treat the file end of the rest of the file equally. And from this issue, we have learned that policy for different circumstances should be harmonious with one each other. Now let's describe the scheduler dependency. Actually, the discovery of this issue is based on an interesting observation. We thought we had controlled all the factors that influence the data layout on disk. And we expect our experiment to be deterministic. But when we repeat the same experiment twice, we find that 6% of these bands are different. And the biggest difference is up to 44 gigabyte, which indicates potentially a very large data layout variation. By data analysis, we find that the randomness only happens when there are two CPUs. Such an observation leads us to the source code that's related to the OS scheduler, and we find out the following. There is some space reserved for each CPU. The data written at that CPU goes to its own reserved space. The motivation of this design is that it can avoid contention for the reserved space. But we find such a design can lead to problems. The problem is when you have two or more CPUs, the flashing thread carrying the data can migrate randomly among these CPUs, depending on OS scheduler, so the data can be spread to many locations on disk. When you have more CPUs, the situation can get worse. To fix it, we simply choose a location based on inode number instead of the CPU ID. From this issue, we have learned that policy should not depend on environmental factors that may change and are outside the control of the file system. Now we have covered the first two issues, and you'll find the rest of issues on the paper. File size dependency means that ext4 chooses its allocation policy based on file size. But since file size can change dynamically, the dependency can become a problem. In normalization bug, a field in the allocation request is updated with a round value, and then the file system looks for a free space in a round location, and then that leads to problems. After removing these issues, we have improved the data layout quality of ext4, and this figure shows the result. X is the disk-span, Y is the cumulative density function. We can see that after our fix, the curve has a much smaller tail. So we do improve the ext4 data layout. But do our fix reduce latency? To find out, we use multiple threads to create 10 files. Each of the files is 64 kilobytes. And the files are highly fragmented because of the schedule dependency. After the files are created, we measure the time to update these files. And this figure shows the result. X is the number of threads that we used to create these files. Y is the update time of the file. You can see that the before curve goes up as you have more threads. But after our fix, the time is almost constant. Our fix reduced latency by up to 1.4 seconds in this case, which is significant for interactive services. So we do reduce latency. To conclude, we have found that statistical techniques are practical for studying file systems, and we have found and fixed for allocation issues in ext4, and our fixes lead to better layout and lower latency at a node, and eventually lead to lower latency at scale. From these issues, we have learned that policies should be harmonious with each other. Otherwise, unexpected issues may happen. And we also find that policy should not depend on environmental factors such as the unpredictable OS scheduler. Most importantly, we find that stats can help you reduce unexpected issues caused by intuitive but unreliable design decisions. And the source code and data online, and you can find all the data and scripts to reproduce all the figures in the paper. Thanks.
So just one question over here. So Justin Zolhuska from Edit Chair. So you talked about, at the beginning, XFS and ext4, but then just concentrated on ext4. So I think that's because you said XFS was a well-behaved file system or something like that.
Within the space I explored. Yep.
So did your tool find anything wrong with XFS? Could you figure out, or is that space just something that is unexplored or for the future?
I did find something weird in XFS, but it's like, because SFS, I think it chooses allocation policy kind of depending on how much space you left. And that sometimes leads to problems, but I haven't dig it in very detail.
Okay,
so, yeah.
Okay, thanks.
Hi, other side, over here. Hi, Keith Smith from NetApp. So your tool obviously did a good job of finding a bunch of tail latencies and giving you the information so you can analyze them. I'm wondering whether, you sort of introduced it with this statistical sampling technique, and I'm wondering whether you feel that this technique uncovers all of the possible tail latencies in your system, or is it just a way to get some low-hanging fruit and maybe some of the search space you don't look at includes others that we should also worry about?
You mean how well the sampling method can cover the overall space?
Well, how well it covers the overall set of problems that cause tail latencies.
I don't know, because to find out, the only method is to do an exhaustive search, so you can see how much you have found comparing to the overall problems. But I think it does a pretty good job in finding those weird behaviors.
No, it's clearly very useful because you found a whole bunch of stuff that will make everyone's life better. But okay, thanks.
Okay, here on this side, Juan Gomez, NetApp. This is very good research. I'm very interested on it. Are you contributing that back to the open source community, that they accepted it, or just curious about that part?
Yeah, I give a talk at Boston in March. I think it's the same talk. Yeah.
Based on the problems that you saw, would the file system tail latencies also occur if you were to allocate the disk space, all of the disk space up front with, say, falloc?
I didn't get the question. Can you repeat?
So I was wondering, based on the problems that you were seeing, does this also occur when you allocate the file space up before you start accessing the file with a function with a system called much like falloc? Fallocate, thank you.
I think with falloc, so if you use, so EX4 has this delay allocation, and I think fallocate behavior should be like that. In that case, I don't think there will be too much problem. So basically, I think no.
All right, thank you.
All right, let's thank the speaker one more time.